Well, the last section of this chapter has to do with acid and base ionization constants and how they're related to equilibrium. And so even though we've already talked about acids and bases, we are going to go back into them just a little bit in this chapter because almost all acid-base reactions, again, are going to be equilibrium reactions. And you will remember that acids and bases ionize, which is what makes them acids and bases. And acids and bases also react with water. Now, they normally do not react completely. There are some really, really strong acids or really, really strong bases that do ionize completely. Again, that's all going to depend on how high the equilibrium constant is. And how much they do ionize, how much they react, tells me how many hydronium ions are going to be present in the solution. And the pH is a measure of how many hydronium ions are in the solution. So the more of this there is, the lower my pH is going to be. The stronger the acid or base, the more it ionizes, the larger the Ka or the Kb. Now this is the acid ionization constant, this is the base ionization constant, and they're going to be expressed the same way that we wrote an equilibrium constant, and I'll show you how to do that in just a minute. So the larger the value, the further to the extremes of the pH scale that particular chemical is going to be. Now remember what we learned about the pH scale. The pH scale ranges from 1 all the way up through 14. 7 is classified as neutral. 1 is acid, and anything between 1 and 7 is acid. Anything between 7 and 14 is a base. The closer you are to 1, the more acidic it is. The closer you are to 14, the more basic it is. Okay, so anything that is close here is going to be a very very weak acid or a very weak base. The more to the extreme, the stronger acids and the stronger bases. So I'm going to make sure I'm out of the way here for just a second. In case you wanted to pause the video and write any of this down, there's some pretty good summary statements there to help you remember everything. And then we will, again, go do a couple of example problems so I can show you exactly how these are going to be ionizing with water. So the first example that we will be using on your example page there is called nitrous acid. It's HNO2. And again, from our acid and base studies, you should recall that an acid is a hydrogen ion donor. And so nitrous acid will react with water. And you'll remember that water is amphiprotic or amphoteric. Both of those words mean the same thing. And it will act either as an acid or as a base depending on what it's in contact with. So this again is an equilibrium reaction. So since this is the acid, this is going to donate a hydrogen ion over here. And so since it's a hydrogen ion, and what's going to be left behind is an NO2 minus because I've taken off the H plus. The H plus is going to join the water and make an H3O plus, a hydronium ion, which is one that you memorized a long time ago. Hopefully you haven't forgotten that. So this is what the ionization reaction actually looks like. So because this is an acid, we can show what the Ka for this is. I did not put my phase symbols up here. I probably should have. This is aqueous, this is going to be liquid, and then ions are going to be aqueous because they are dissolved in solution. So for your Ka, you're going to have, this is called a nitrite ion. This is not one that you memorize, but it is a nitrite ion, the hydronium ion, all over the nitrous acid. Okay, and the water, because it's a liquid, we don't include that in the equilibrium expression. So you can see that the Ka is, you find it the same way that you found an equilibrium expression. The only difference is that we call it a Ka because it is specifically for an acid. Okay, so that's the equilibrium expression, the ionization constant. It says that the ionization constant is equal to 4.5 times 10 to the minus fourth. They want to know if that's stronger or weaker than acetic acid, that's the acid that's in vinegar, which is 1.8 times 10 to the minus fifth. Well, the stronger the acid has the bigger Ka. So if you are comparing this Ka, which again was 4.5 times 10 to the minus fourth molar, to that of acetic acid, whose Ka was 1.8 times 10 to the minus fifth, which one of these numbers is bigger? Well, this one is bigger because of the size of the exponent. This is a minus 4, this is a minus 5. Okay, so because this number is bigger, that means that the nitrous acid is going to be stronger than the acetic acid. So this one here is your stronger acid. Okay, and you can tell that just by looking at the ionization constant. Again, the bigger the number, the more it ionizes, the more of this you have in solution, the stronger the acid is, because the lower the pH is going to be. Okay, so that's an acid. Let's look at a base now. If an acid is a hydrogen ion donor, a base is going to be a hydrogen ion acceptor. pH 3 is a base. And again, I should probably make sure that I get my base symbols written up here. It's going to react with water. If an acid is a hydrogen ion donor, base is a hydrogen ion acceptor. So because the water now is in the presence of a base, it's going to be the one to donate a hydrogen ion. So the hydrogen ion is going to go this direction, which will give me pH 4 with a positive charge. When I take a hydrogen ion off of here, that leaves me with an O and an H and a negative sign. Okay, so a hydroxide ion, which again is one that you've memorized. So because we already know that this is a base, I'm going to call this equilibrium expression my Kb. And this is going to be expressed as pH 4 plus times OH minus over concentration of pH 3. Okay? Now you may be looking at that and going, I don't quite understand how, where's the H3O plus in that? Because pH is supposed to be related to pH, which is hydronium ion concentration. He doesn't mention this in the book, but I'm going to try to explain to you what happens here. When you have water, if I have two waters, those waters can ionize by themselves. Okay, so I can end up with an H3O plus and an OH minus if one of my waters will donate a hydrogen ion to the other one. So what's going to happen is that depending on what increases in solution, if you have more of the hydroxide ions, you're going to have fewer of the hydronium ions because it's a balancing reaction that is going to go back and forth like this. So if the hydroxide ions go down, the hydronium ions go up. If the hydronium ions go down, the hydroxide ions go up. So if you are increasing this, that means you're going to be decreasing the hydronium ions, and so that is how the pH is affected. If you go on to take college chemistry or another course in chemistry while you're still in high school, you'll talk a lot more about pH and acids and bases and how you actually calculate pH from concentration, but we're not going to do that in this particular class. Okay, so that was the Kb for that particular reaction. Then we have one more problem to look at, and it says that you've got equal concentrations of aqueous solutions made with 4 different chemicals. And that's really an important point to grasp, is that because your acids can be stronger or weaker, your bases can be stronger or weaker, the concentration can be the same. You can have 1 molar solutions of a whole bunch of different chemicals, and even though they may all be acids, that doesn't mean that they're all equally potent. And the reason for that is because they each ionize a different amount, even though the concentrations may be the same. So it all has to do with how much they ionize. So the pH of the solution is written next to the chemical formula. You can see that on the problem in front of you. We want to identify the acids and the bases, indicate their relative strengths, and the relative sizes of their Ka or their Kb. Okay, so the first thing I'm going to do to solve this problem is I am going to list the acid, or list the pHs in order. So the smallest pH that I have is 1.0. The next size up is a 5.1. From there I go to an 8.7 and then to a 13.5. Okay, so now that I have the pH listed in order, now I'm going to put which chemical that is. So the pH of 1 was related to the HBr. The 5.1 was C6H6OH. The 8.7 was C2H7N. And then the 13.5 was KOH. Okay, so that just came straight from the problem. All I've done so far is I've listed the pHs in increasing order. Okay, so now we need to look at what's an acid and what's a base. Well, if you recall, anything less than 7 is an acid, and the closer I am to the extremes of the scale, the stronger the acid is. So if I'm comparing these two are acids. In comparison to each other, this one is a very strong acid, while this one will be a very weak acid. Okay, these are both have a pH greater than 7, and so the further I am to the extreme is the strength of the base. So since this is the closest to the 14, this is going to be a very strong base. This one's pretty close to neutral, so it's going to be a weak base. Okay, and I get that just based on where they are on the pH scale. So how does that relate to their Ka or their Kb? Well, the stronger the acid, the larger the Ka. So that means if I had Kas to compare, this would have a large Ka, and in relation to this one, this would be a small Ka. Okay? Same thing is going to be true on this end. The stronger the base, the larger the Kb, and the weaker the base, the smaller the Kb. Okay, so that is how you can tell the difference just by looking at ionization constants, and you can determine whether an acid or a base is weak or strong depending on that constant, and you can relate that to where it's going to fall on the pH scale as well. Generally, anything that's going to fall on like a 1 or a 2 is going to be considered a very strong acid. Anything that's up in the 13-14 range is going to be considered a very strong base. Others are going to be weak acids or weak bases, and the closer they are to the neutral point, the weaker they're going to be.